Good day to everyone. Today we are going to discuss Module 4 of the subject CE 3151, Lecture and Laboratory. Topic is Systems of Linear Algebraic Equations. An introduction. A system of linear algebraic equations, or simply called a linear system, is a collection of one or more linear equations involving the same set of variables. So given the following equations, we have 3x plus 2y minus z equal to 1, 2x plus 2y plus 4z equal to negative 2, and negative x plus 1 half y minus z equal to 0. These three equations now is a system having three variables, x, y, and z. A linear algebraic equation or a linear equation that is an algebraic equation having a first degree in all its unknown. So as you can see in our examples here, all of our variables are in its first degree, meaning these equations now would represent a line when we try to draw it in a graph. So the general form of a linear algebraic equation would follow a1 x1 plus a2 x2 plus en xn is equal to b, wherein the values of a are the values of the coefficients, and x1, x2 until xn would represent now our unknowns or your variables. And b here is our constant. The general system for any number of linear equations, m, with any number of unknown n can be written as a11 x1 plus a12 times x2 plus a1 n xn is equal to bn until a number of equation until m. So they would follow the same format or general form of your linear equation, but will have several or a number of equation m. And these equations now can be written as a vector equation, wherein each unknown is written as a weight of a column vector in a linear combination. So we could have, for your first variable x1, this now can be written as a column vector x1 times a11, 21, m1, which will now be the first column of our matrix later on. Same goes for your second variable. It will be a weighted column vector now for its equivalent variables or equivalent coefficients. As we have converted linear equations into a vector equation, these vector equations now can also be converted into a matrix equation, which is now equivalent in the form of ax equal to b, wherein A is any m by n matrix, x is the column vector of the n entries, and b is the column vector of your m entries. So given now vector A, which will be consisting of the coefficients, and x will be equivalent to the matrix of your variables, and b is given by the matrix of the constants for each equation. In solving systems of linear algebraic equations, we now have what we call your solution set, which is simply the set of all possible solutions. This now is a solution for a linear system, is an assignment of the values to the variables x1 until xn. The solution for a linear system may behave in any of the following. It can be a consistent system, which will have at least one solution and can either be categorized as an independent system, in which it will have a single unique solution, or a dependent system, which will have infinitely many solutions, or it can also be an inconsistent system, wherein the linear system will not have any solution. The properties of a system of linear equations would be defined by its independence, consistency, and equivalency. So when we say independence, if none of the equations of a linear system can be derived algebraically from the other equations, then it means that the equations are independent from each other. Independent equations will each contain a new information about each variables. Removing any of the equations in our system would now increase the size of our solution set. For consistency, any homogeneous system with no solution is considered inconsistent. Otherwise, if the system will have solution, at least one solution, then it is a consistent system. For equivalency, two linear systems will be considered equivalent if and only if every solution of either system is a solution of the other equation or of the other system. The solution sets for a linear system could either be a trivial or non-trivial solution. For a trivial solution, this would simply be defined as the simplest solution of any equation. Thus, a solution set of a homogeneous linear equation will follow these conditions. The variables of the equations would all have zero value. x1, x2, x3 until xn will have no value, and that the determinant of the matrix A is not equal to 0. For any matrix, it will also follow that all the values of your x will also be equal to 0. For non-trivial solutions, the system of equations now in which determinants of the coefficients is equal to 0 will be considered a non-trivial one. This will now involve non-zero solutions or examples. And the determinant of the matrix A should be equal to 0 in cases wherein it will have a non-trivial solution. There are different methods for solving a system of linear equations, and this would now include elimination of variables, which is the simplest method for solving linear systems, row reduction, or also known as the Gaussian elimination. The linear system now in our solution will be represented as an augmented matrix. Another method is the solution by inversion. One method under this is the inversion by Gauss-Jordan and by adjoints. Another method to solve for your linear systems will be Cramer's rule, which is an explicit formula for the solution of linear systems, and the matrix solution and other methods. So for Module 4, we will be discussing row reduction, solution by inversion, and Cramer's rule. So that's it for the introduction of systems of linear algebraic equations. For the next lecture, we'll be starting with row reduction. Thank you for listening.